Welcome everyone. We'll start talking about input-state linearization. What we are going to do this time actually is first to derive an algorithm to convert a given nonlinear model to the controllability form. Then second, we'll apply that to an example of a single link manipulator with flexible joins. I'm exactly following actually the reference Nonlinear Systems by Khalil. Now let me first mention here that if we define a transformation, like for example, suppose we have the original states x and we have a transformation that converts x to another space defined by state variable z, then if that transformation t, which is a map, is continuously differentiable, and also its inverse, which means that if we like to calculate x, it should be the inverse of t for z. If its inverse is also continuously differentiable, we call that kind of transformation or map diffeomorphism. So this is a terminology used frequently in feedback linearization literature. Now, let's see how to develop an algorithm in order to find the transformation T that would help us design a controller. Let me say at the beginning that the transformation is not unique, and this is similar to the case of linear systems where you could have several transformations. So we will consider just one algorithm here for a specific kind of a transformed system, which is the controllability form. This is one thing. Second, in our analysis here, we are assuming full state feedback, which means that all states will be available for feedback. Now I'm going to consider the differential equation x dot equals f of x plus g of xu, where x here is a vector of dimension n, f and g are nonlinear functions, and u is the control signal and the input of this system. That means that f maps a specific domain in the x space into the nth dimension real space, and similarly g is also a map from a specific domain in the x domain to the nth dimensional real space. That actually implicitly means that I'm talking about a single input system. This is just for simplicity. However, the procedure actually can be generalized for a multi-input system as well. As I mentioned before, the transformation that I'm considering would be a map from x to z, and consequently, if we take the derivative of z, that would be the partial derivative of t with respect to x times x dot, and here I can substitute for x dot from the original system equation. So that would give me the partial derivative of t with respect to x times f of x plus the partial derivative of t with respect to x times g of x times u. So this would be the transformed state space equation. Now the question is how to find the transformation T. Okay, in order to do that, I'm going to assume that I'd like to have a specific form in the transformed domain, and that form is the controllability form. So z dot would be equal to AC in the controllable form. BC here is a vector in the controllable form, and then the input and nonlinear functions alpha and beta. Alpha and beta are nonlinear functions that we are going to derive through the algorithm. And if we manage to do this, we can design U so that the transformed system would be in linear form, and consequently you can select the closed loop dynamics as we wish, maybe using state feedback as we have done before. The controllable form would have the A matrix in this structure, where here we have an identity matrix of dimension n-1, while the whole A matrix is of dimension n by n. Here we have a column of zeros, and the last row here is also composed of zeros. This is the form of the A matrix. The B vector would have all 0 elements except the last element, which is 1. The transformation Z will be composed of n functions, t1 up to tn, and each of them is a function of the state variable vector x. That means that if we compare this equation that we would like to have with the original system equation that we have derived based on the transformation, I'll first put the required form in a specific structure so that we can do the comparison easier. I will put it, I'll collect terms that don't include u together. So I will have here ACZ plus BC times minus alpha of x divided by beta of x. So this is the term that doesn't include u, and then this will be plus the vector b times 1 over beta of x times u. Now I compare this form with the form that we have derived before for z dot, and then I will conclude the relations that will be used to calculate the transformation t. So what we have is z dot equals partial t partial x times f plus partial t partial x times g u. So I like to have this term and this term to be similar. So I will do that element by element. Now remember the structure of AC, it is in the controllable form, which means that when I multiply AC by Z for the first, say, row, I will get just the second element of the vector Z, which is Z2. And Z2 is nothing but T2. So consequently, I can write T2. Here, the vector B, it has the first element equal to 0. So the term that multiplies minus alpha over beta is 0. So the multiplication then would just give me T2. And that has to be equal to the first element in the partial derivative of t by x times f. And that would be the derivative of the first element here, t1, with respect to x times f. This is of course the gradient vector, and it would be composed of partial t1 partial x1 up to partial t1 partial xn times the vector f. So this will be the first element that I get from the multiplication of AC by Z. The second element will be similar. I can calculate T3. That will come from the second row, because AC times Z will give me, if I consider the second row here, that will give me T3. And again, the vector b, the second element in the vector b is 0, so that it will not appear in this expression. And that should be equal to partial t2 partial x times f, and this is the second row here in the vector z. And I can generalize this actually, that the partial derivative of the ith component of t with respect to x times f, that will give me this next component of t, which is t subscript I plus 1. I can continue that till I reach, here I would go from 1 up to n minus 1. If I like to calculate the last term, which is the partial derivative of tn with respect to x times f, we will notice that this will be equal to minus alpha over beta. That's because the last row here in the vector A is 0, and the only result that I would get from the first component here would be coming from the product of BC times minus alpha over beta. And since BC all zeros but except the last element, so the last element is minus alpha over beta. So that gives me the last expression here. I will do the same procedure for the second term here, the term that multiplies u. So partial t partial x times g should be equal to the vector bc multiplied by 1 over beta. However, again, I notice that the b vector is composed of all 0 elements except the last one. That means that all the components, the right hand side, if we put say partial t partial x times g equals to bc times 1 over beta. So we'll notice, since b is composed of all zeros except the last one, then the first n minus 1 components will be equal to 0. That means partial t partial x times g will be 0, partial t2 partial x times g will be equal to 0, and so on up to partial tn minus 1 partial x g equal to 0. The last component would be the partial derivative of the nth component of t with respect to x times g, and that would be equal to 1 over beta. So actually now I have a procedure to compute the transformation t, and once I compute the transformation t, I can calculate beta and alpha. The procedure is summarized as follows. The partial derivative of ti with respect to x times f is equal to ti plus 1, and this is for I 1 up to n minus 1. So this is the first equation. The second equation is that the partial derivative of the nth component of t with respect to x times f, that should be minus alpha over beta. For the partial derivative of t I with respect to x times g, we will get 0, and that for I from 1 up to n minus 1. And the last component, the nth component of t, partial derivative of that with respect to x times g, that will give me 1 over beta. So these actually the basic equations that we can use to transform a given nonlinear system into the controllability form. Then we have to solve these equations for t1 up to tn. Once we do that, we will be in a position to calculate the control signal. we can take the control signal u as alpha x plus beta v, where v can be designed to locate the closed loop poles of the controllability form in locations that we specify, and consequently we achieve stabilization of the system. To illustrate the implementation of the above algorithm, I'm going to consider an example of a single link manipulator with flexible joints. So it's given by this standard differential equation x dot equals f of x plus g of x u, where f and g are vectors given here. This is the expression for f and this is the expression for g. And the vector x is composed of 4 components, x1 up to x4. I'm assuming here that the constants a, b, c, and d are positive, real and positive. We can show easily that the equilibrium point for this nonlinear system would be at the origin. Now I'm going to state the equations to be implemented. We know that the order of the system is 4. So I can write then the following equations for the components t1, the partial derivative of t1 with respect to x times g, that will be equal to 0. The same for the second component of t times g equal to 0. The third component times g equal to 0. The fourth component of t with respect to x times g, that would be 1 over beta. So these are the 4 equations related to g, and we have other 4 equations to related to f. So it is partial t1 partial x times f, that will be equal to t2, partial t2 of x times f equal t3, and partial t3 partial x times f, that would be t4, and finally the partial derivative of t4 with respect to x times f, that would be minus alpha over beta. So let's implement these equations and see how to derive t1 up to t4. From the first equation here, we know that the partial derivative of t1 with respect to x times g would be the gradient of t1, so that's partial derivative of t1 with respect to x1, partial derivative with respect to x2, partial derivative with respect to x3, partial derivative with respect to x4, and g is 0, 0, 0 times d. So that will give us d times the partial derivative of t1 with respect to x4, and that has to be equal to 0. Of course, d is a positive constant, so that we are only left with the condition that this partial derivative has to be equal to 0. And then we conclude that t1 is independent of x4. So x4 will not appear in the expression of t1. Now we'll move to this equation as a second equation to apply. So we'll multiply the partial derivatives of t1 times f. Now again, the partial derivative of t1 with respect to x, this would be the gradient vector, but this time I'm going to multiply by f. So every component here will be multiplied by the corresponding component in the vector f. However, we know that the last component is equal to 0, so it will not appear in the product. So what I get then, that t2 would be equal to the partial derivative of t1 with respect to x1, and this is times x2 plus the partial derivative of t1 with respect to x 2, and that's times minus a sine x1 minus b times x1 minus x3, and then partial t1 partial x3, and that's times x4. So this is the second component. Now I'm going to implement this equation. That the partial derivative of t2 times g is equal to 0, and again partial t2 partial x times g equal to 0. That will also lead to the partial derivative of t2 with respect to x4 equal to 0. This is similar to what we have done with t1. So that means that t2 is independent of x4. Now if we look here to the equation of t2, we'll find this term which depends on x4. So we don't want t2 to be dependent on x4 according to this condition. Now the only way to force this condition to be true is that to take t1 independent of x3. So we conclude here from that condition that t1 is independent of x3. So now we know that t1 will be independent of x4, and t1, sorry, this is t1, and t1 is also independent of x3. So we continue by requiring the partial derivative of t3 partial x times g equal to 0, and that requires the partial derivative of t3 with respect to x4 to be equal 0. So t3 has to be independent of x4. But what is t3? It is the partial derivative of t2 partial x times f. So if we do this, we get the partial derivative of t2 with respect to x1 times x2 plus partial derivative of t2 with respect to x2, and that's multiplied by minus a sine x1 minus b x1 minus x3 plus the partial derivative of t2 with respect to x3 times x4, and we know that the partial derivative of t2 with respect to x4 is equal to 0, so it will not appear in the expression for t3, because we have mentioned before that t3 is independent of x4. However, since t3 is independent of x4, then also this term shouldn't appear, because x4 appears here. So we require then that t2 to be independent of x3. That will lead to the partial derivative of t2 with respect to x3 to be equal to 0. But if we look at the expression for T2. This is the expression for T2 here. We will find that T2 depends on x3 here, and that multiplies the partial derivative of T1 with respect to x2. So in order to force T2 to be independent of x3, we will require T1 to be also independent of x2. So that will lead to T1 independent of x2. So we have T1 independent of x2, independent of x3, and independent of x4. That will leave T1 to be only dependent on x1. So we select T1 to be equal to x1. Now the only thing that we will require from the function of T1 is that it would be 0 at 0, which means if you put x1 equal to 0, you get a value equal to 0. That means that this is not actually a unique choice for the function T1. It is just a simple one. But if we take, say, x1 equal to x1 squared or x1 cubed, we still get the same result. We could even have x1 plus x1 cubed, for example, as for T1. Once we calculate T1, we can go forward and calculate T1 up to T4. So T2 actually is the partial derivative of T1 with respect to x times f. Now this will give me, since T1 is just x1, so the only components that will exist in the gradient will be the first component. It will be 1, then zeros, and that's times f. So that will lead to x2, and we can calculate T3 as the partial derivative of T2 with respect to x times f, and that will give us minus a sine x1 minus b x1 minus x3. And finally, we can calculate T4 to the partial derivative of T3 with respect to x times f. And that will give us minus a cosine x1 minus b times x2 plus b times x4. So that is the transformation. Then we can write expressions for z1, z2, z3, and z4, because z1 is just t1, z2 is t2, and z3 is t3, z4 is t4. So this is x1, this is x2, this is minus a sine x1 minus b x1 minus x3, and this is minus a x2 cosine x1 plus b x4 minus x2. So this is the expression for it. Now, in order to find the state space representation in the controllable form, we know that in that representation z1 dot will be just z2, z2 dot will be z3, and z3 dot will be just z4. This is the controllable. And z4 dot would be equal to, I will just take the derivative of z4, the expressions that we have here. So we'll take the derivatives of the different terms here. So that would give me minus a times x2 times x1 dot sine x1 plus x2 dot cosine x1 plus b times x4 dot minus x2 dot. Now I'll go to the original equations of the system and substitute for x1 dot, x2 dot, and x4 dot. Here x2 dot is repeated, so I will substitute for that as well. So if we do that substitution, we get minus a times minus x2 squared sine x1 plus minus a sine x1 minus b x1 minus x3, that multiplying cosine x1 plus b times c x1 minus x3 plus du minus a sine x1 minus b x1 minus x3, that covers it. Now we'll notice here that this term is nothing but z3. This is again z3, and we know that x1 is equal to z1. So also x2 is z2. So we can rewrite the equation as minus a times z2 square minus z2 squared sine z1 plus z3 cosine z1 plus b times c, this multiplies z1 minus x3 plus du minus z3. So this is the last term. So we only have to find an expression for x3 in terms of the new coordinates. We know that z3 is equal to minus a sine z1 minus b z1 plus b x3. So from that we can find an expression for x3 to be z3 plus a sine z1 plus b z1. This is divided by b. And if we substitute that back in the equation for z4 dot, we get the final equation that z4 dot equals minus z3 times b plus c plus a cosine z1 plus a times z2 squared minus c sine z1 plus bd. So this is the form that we would like to have, and of course we can then use the control signal u to linearize the system if we like. So based on the new transformation, this is what we called before 1 over beta, and this is the expression for minus alpha over beta. So now we can select the control signal to linearize the system in the controllability form, and maybe place the closed loop poles in the new coordinates in a location that we desire. So the above summarizes a technique that can be used to linearize a state space system in the representation and put it in the controllability form. Thank you.